A drop of oil is modelled as a circle of radius r. At time t, r equals 4 times 1 minus e to the power minus lambda t, where lambda is a positive constant. Show that the area of the circle satisfies this equation. So the area of the circle, so area is pi times the radius squared. So I could, if I wanted to, differentiate this with respect to the radius. So I could say that that's 2 pi r. So I know how the radius is changing with respect to I know how the area is changing with respect to the radius, but I want how the area is changing with respect to time. But that's fine, because I can do this by connecting the rates of change. I can call this dA by something times something by dt. And given what I just wrote down above, this is going to be dA by dr, which means this has to be dr by dt. So what about this dr by dt? Where's this going to come from? Well, let's take our radius expression. To differentiate this, to make my life a little bit easier, I'm going to expand those brackets, first of all. So 4 times 1 is 4. The 4 times the minus e to the minus lambda t. Right, let's differentiate that. If I differentiate the 4, it's going to be 0. So we're then going to get minus 4. Now the exponential will differentiate to be the exponential. But by the chain rule, I need to multiply this by the derivative of the inside function. The derivative of minus lambda t is minus lambda. So that's going to become minus 4 times minus lambda is positive 4 lambda e to the minus lambda t. So substituting those into my expression, I've got the 2 pi r multiplied by the 4 lambda e to the minus lambda t. So I've got an expression for dA by dt. I'm now looking to see if I can write it in this form. I can see at the moment that I've got 8 pi r times lambda. So 8 pi lambda r, and then I've got I've got an r in my answer. They don't. But that's fine, because I can replace that r with this. So 8 pi lambda multiplied by 4 minus 4e to the minus lambda t multiplied by the e to the minus lambda t. I can factorise the 4 outside, which would make it become a 32 pi lambda. And then I can multiply each of these by the e to the minus lambda t. Leave the 32 pi lambda at the front, because that's going to match up with what we're trying to show. The 1 times e to the minus lambda t is e to the minus lambda t. And the e to the minus lambda t times the e to the minus lambda t, just adding those powers together, we'll get e to the minus 2 lambda t. And that's what we needed to show. Moving on. In an alternative model of the drop of oil, its area at time t satisfies this equation. Given that the area of the drop is 1 at t equals 1, find an expression for the area in terms of t for this alternative model. So we need to solve this equation. So we need to separate the variables. So I want the a's on the left-hand side. So I'm going to take this a term here and divide on the left-hand side. So I'd get 1 over a to the power of 3 over 2 dA. So those are all of my a terms on the left-hand side. I'm then going to take the t terms and have them on the left-hand side, right-hand side. So this is going to come over here, and the t squared on the denominator will stay exactly where it is. So there we go, we've got a's on the left-hand side, we've got t's on the right-hand side. Now to integrate both sides, I'm going to rewrite the powers on the numerator with a negative power. So that I can add 1 to each of them and then divide by the new power. So minus 3 over 2 plus 1 is minus a half. When I divide by minus a half, well, dividing by a half is the same thing as timesing by 2. So this is timesing by minus 2. On the right-hand side, add 1 to the power. Minus 2 plus 1 is minus 1. Divide by minus 1. And not forgetting the plus c. Right. We were told that the area was 1 when t is 1. So let's substitute that in. So, if a equals 1 when t equals 1, we'll get minus 2 times 1 to the power of minus a half equals minus 1 to the power of minus 1 plus c. Now, 1 to the power anything is going to be 1. So this is just going to be minus 2. And again, 1 to the power anything is going to be 1. So therefore, c equals minus 1. And we can then say that my equation minus 2a to the power of minus a half is equal to minus t to the power minus 1 minus 1. Right, let's multiply all the way through by minus 1 to get rid of these negatives. And let's make a the subject. Now, to do this, I don't like these negative powers, so I'm actually going to rewrite these as positive powers like that. This might give me a clue as to what to do next. Now, what I'm going to do is I'm going to get a common denominator on the right-hand side, so I'm going to rewrite that. So it'd be 1 over t plus t over t, which is the same thing as 1 plus t over t. That's a good thing to do because, remember, I'm trying to make a the subject here. So now what I can do, let me just make that. I can do the reciprocal of both sides. So I get a to the power of a half over 2 equals t over 1 plus t. Now I've got the a on the numerator, which I like. Times both sides by 2. And then square both sides to get a by itself. So 2t squared is 4t squared over 1 plus t all squared. And that is my expression for a in terms of t for this alternative model. That is my answer for part B. Now for part C. Show that in the alternative model, the value of a cannot exceed 4. So let me just clear a bit of space. Now, cannot exceed 4, so I want to talk about what happens when t becomes large here. In order for me to say as t tends towards infinity, I don't want the t appearing in the numerator and the denominator. I want it only appearing in one of them, otherwise it's too complicated. So I'm going to actually rewrite my answer from part B to make it a little bit simpler. To help me, I'm going to expand the denominator. And then I'm going to divide top and bottom here by t squared, so that I only have t's on the denominator and there won't be any t's on the numerator. So my denominator then will become 1 over t squared plus 2 over t plus 1. And the good thing now is I can say that as t tends towards infinity, 1 over t squared will tend towards 0. Also, 2 over t will tend towards 0. So both this term and this term will tend towards 0, which means that a will tend towards 4 over 0 plus 0 plus 1, which will tend towards 4, which I needed to show that. So I can say that the area will tend towards 4, but never exceed it.